So let's draw some pictures of these ideas of one-sided continuity. So let's say I had the following. Maybe I got a segment of a curve coming in over here, and then it stops, and I got an empty dot there. And then I got another hole down here. And let's say I had something like that. Okay, and this is a point, let's say, a real number a. Now, that function is definitely not continuous at the point x equals a. You can see, just in the traditional sense of the word, you have to, if I trace the curve, I can't get to here without jumping. And in fact, the limit from the left as x approaches a, and the limit from the right as x approaches a of the function, whatever function this is the graph of, are going to be different. But if I were to fill in the dot here, then now, all of a sudden, the function is defined at a. And the output from the function at the point a is equal to the limit of the function as x approaches a from the left. In other words, it satisfies this definition here of being continuous from the left. Right? The limit from the left of the function is equal to the actual value of the function at the point x equals a. Okay, so this is the picture of what that would look like. So this is continuity from the left at x equals a. That's just a picture of what it would look like. And let's draw a picture of continuity from the right. It's the same idea, but we can draw a picture of that too anyway. So same situation. Let's say we've got an empty dot on the end of every segment, and then we'll shade in a dot afterwards. Let's say you've got that situation. Again, that's a function that's not continuous at x equals a. It's in fact not even defined at x equals a. But if we were to add a definition for f of a by filling in the dot here so that this is a solid dot, well, now you have the fact that the function's value at a is equal to the limit of the output values as x gets close to a from the right. The y values of the points in the curve approach whatever the y value is at this point, and that's what it means to be actually continuous from the right when that dot is solid. So this is continuity from the right at x equals a. Okay, so that's a picture of what those terms look like. Let's look at what it looks like in practice. Here's a function. We've got a piecewise function h defined in the following manner. H of x is defined to be x plus 3 for values of x that are greater than or equal to 5. And h of x is equal to x squared minus 1 if x is less than 5. So my claim is that this function is continuous from the right, but not continuous at the point x equals 5. So it's continuous from the right at x equals 5, but is not just continuous in the ordinary sense of the word at x equals 5. And in this example, we're asked to check that. Okay, and whenever you're doing these types of questions, when you're basically, this is a perfect example of what it means to investigate the continuity of a function near a point, or at a point. In this case, the point is x equals 5. But whenever you do this, you're just going to take both of the one-sided limits, one at a time. So limit from the left as x approaches 5 of h of x, then take the limit as x approaches 5 from the right of h of x. But then also calculate the actual function's value at x equals 5. So you actually plug in x equals 5 and see what you get. So you're going to calculate those three values and see how they compare. So let's start with the limit as x approaches 5 from the left of h of x. Okay, let's see what we get. Well, how do you start ones like this? How do you start with a piecewise function? Well, the first step is to figure out what is h of x actually doing. And as based on this rule, it depends on where x falls. If x is greater than or equal to 5, h of x is going to behave like x plus 3, right? If x is less than 5, then h of x is going to behave like x squared minus 1. So which one is it? And for that, you look down here. Because x is approaching 5 from the left, that means x is smaller than 5, right? So that means for this limit, h of x might as well just be the function x squared minus 1. So that's your first step. Write this as the limit as x approaches 5 from the left. Nothing else will change, but we're going to replace h of x with x squared minus 1. And now, well, you have the limit of a polynomial. Just who cares about h now? This is the limit we're working with now. And if you have a limit of a polynomial, remember polynomials are continuous on their domains. And their domains are everything, so they're certainly defined at 5. So just plug in 5 and you get the answer. So you're going to get 5 squared minus 1, which is 25 minus 1, or in other words, 24. Okay. Now what about the limit as x approaches 5 from the right? Well, that's the other one-sided limit. We have to work that one out as well. And we're going to use the same strategy, right? Start by figuring out what h does. Well, as x approaches 5 from the right, that means the values of x are greater than 5. Right? So h of x is going to behave exactly like x plus 3. So we'll get the limit as x approaches 5 of x plus 3. And now, well, again, you've got a polynomial. It's a linear function, but it's still a polynomial. So plug in x equals 5 and you can get the limit, because this is a function that's continuous at every real number. In particular, it's continuous at 5. So go ahead and plug in 5. You'll get 5 plus 3, which is 8. Okay, and that's enough to know. Right off the bat, part of this is already done. The second part, right? We wanted to show, first of all, that h is continuous from the right at x equals 5. We haven't shown that yet, but we also need to show that it's not continuous at x equals 5. Well, if these two limits are different, that's already enough to say that the function's not continuous at x equals 5. Because remember, to be continuous at 5, here's the definition in the case where the function's name was f. You need the limit from the left to be equal to the limit from the right, and those two quantities have to both agree with the actual function value at the point. So in our case, think of a as 5. Well, we've already shown that the two one-sided limits already don't agree, so it doesn't even matter what h of 5 is. It can't be continuous at 5. But let's work out h of 5 anyway, because we do need to show that it's continuous from the right. So what's h of 5? Well, plug in 5 to function h. How do you plug in a point to a piecewise function, right? Figure out which one of these is satisfied when x is equal to 5. 5 is greater than or equal to 5. This one is satisfied and this one is not. So that means we're going to use the definition of x plus 3 here as our definition of h of x. Pardon me, we're going to use x plus 3 as the definition of h of x, and we're going to plug 5 into that, so we're going to get 5 plus 3, which works out to be 8. Okay, so, well, hey, this is the function value, and this is the limit from the right, and they both are equal to 8. So really, that's this situation. That's continuity from the right. So this is your work always when you're doing these types of questions, right? So you just take the limit from the left, take the limit from the right, and the function value, and carefully work them out. This should be a key example in your notes. Bookmark this and keep it handy, because you're going to need to pull this up to do some other problems, especially or to do some of the exercises in the continuity section. Let's summarize what we found. So therefore, I haven't used this symbol in a while, but remember there's 3 dots like a triangle. That's a shortcut to write the word therefore. So therefore h is continuous from the right at x equals 5, but is not continuous at x equals 5. And that's the conclusion that we were asked to draw. So I'm just going to put a box around that, because that's really just concluding the very thing we were asked to show, but our work is right above that, right? And it follows directly from our work, so no more explanation is needed. If you write your work out clearly like that, you don't even need to say anything else. Okay, we've seen 2 different kinds of discontinuities in this section so far. We've seen removable discontinuities, and we've seen infinite discontinuities. In this case, this is an example of the third type of discontinuity we're going to talk about, which is a jump discontinuity. So this is an example of a jump discontinuity, which occurs when the limit as x approaches a from the left of f of x is not equal to the limit as x approaches a from the right of f of x. So in other words, the two one-sided limits don't exist, or pardon me, don't agree, but they do both exist. So I said that wrong. Let me clarify. So a jump discontinuity occurs at a point x equals a when the two one-sided limits don't agree. But then this part afterwards says, but they do both exist. So the picture you should have in mind, really just have these pictures in your head, right? Something like this, where if you're tracing the curve, you have to make a jump, right? The limit from the left is equal to, it exists. Whatever the y-coordinate of this point is, you could find it over here on the y-axis. I don't know, maybe it's 2 or something. But in this picture, the limit from the right exists, and the limit from the left exists too, whatever the y-coordinate is at this point. But they're not the same. So that's why you have that jump there. So this is the picture of what a jump discontinuity would look like. You can imagine why, because if you trace the curve, you'd have to do a jump. But this is the formal definition. If the one-sided limits don't agree, but they do both exist.